Imagine a vector u and a vector v in a two-dimensional plane. We can define the projection of u onto v using the dot product. If the vector v is a unit vector, we find that the projection of u onto v is simply the component of u in the direction of v. We can similarly find the projection of u onto another unit vector w that is orthogonal to the vector v. If we add the two components of u, the two projections, we get the vector u itself. And this can be generalized for any two unit orthogonal vectors in the plane. We know that the two vectors v and w are orthogonal since their dot product is 0, and that each one is a unit vector since its magnitude is 1. We say that these two vectors span the entire two-dimensional plane, and for every vector u in the vector space R2, we can write the vector u as a linear combination of its projections on each vector. The set of those two vectors is thus an orthonormal basis for R2, two orthogonal unit vectors that span the space. And in general, for any vector space V that has an orthonormal basis V, if V is a vector in V, we can write V as a linear combination of the basis vectors, where each basis vector is scaled by the coordinate of V in that vector's direction. Those coordinates are simply the dot product in simple Euclidean vector spaces, but for more general spaces, we define a generalization for the dot product, an operation called the inner product of the two vectors. An inner product should satisfy some fundamental axioms that are consistent with the idea of a dot product. Vector spaces that has some inner product defined on them are called inner product spaces. An example of such a vector space is the vector space of all square integrable functions. The inner product is a very powerful tool because it allows us to generalize the notions of length, angle, orthogonality, and many other properties associated with Euclidean spaces to arbitrary vector spaces. One example is the norm of a vector, which is a generalization of the notion of length in the physical world. We can therefore see that all square integrable functions have a finite norm with respect to that inner product. By investigating the following results, we find that harmonically related sinusoids, which are sinusoids that have frequencies that are integer multiples of some fundamental frequency, are orthogonal to each other. We conclude that the set of those sinusoids and the constant function 1 over root 2 is an orthonormal basis for the vector space that they span. Mathematicians have found that this set actually spans the entire vector space of square integrable functions. And we can therefore write every square integrable function as a linear combination of those basis vectors, each scaled by the function's coordinate in that direction. By expanding the function as an infinite sum of its projections onto the basis vectors, we get the familiar Fourier series expansion of the function on the interval. This method can be used to expand all square integrable functions, even the ones with discontinuities. If we did this sum for a finite value of basis vectors, we get what we call a Fourier approximation of the function on that interval. Since sinusoids are periodic functions, the Fourier series actually give us the periodic extension of any function outside the interval it was originally defined on. But sinusoids are not the only orthonormal basis we can use. Using Euler's formula, we can reach a more elegant form of the Fourier series, the complex exponential form. Exponentials also form an orthonormal basis for the vector space of all square integrable functions. This form is especially useful for generalizing the Fourier series representation to aperiodic functions, defined on the entire real number line. By taking the limit of the Fourier series as the interval grows, we get the Fourier transform. One last surprising geometrical aspect of Fourier analysis is the generalization of the Pythagorean theorem to different function spaces. For any complete inner product space V that has an orthonormal basis, the squared norm of any vector in V is equal to the sum of the squares of its coordinates. This is called Parseval's identity, which is used in signal analysis to calculate the average power of signals, which is equal to the sum of the squares of the exponential Fourier series coefficients. Remember, Fourier analysis isn't just about equations, it's about geometry, symmetry, and the hidden beauty of functions. Whether you're exploring sound waves, heat diffusion, or quantum mechanics, keep your eyes open for the geometrical magic woven into the fabric of mathematics.